Welcome back. In this video, we're going to be looking at example problems of calculating the fluid force on horizontal and vertical surfaces submerged in fluids. Let's get to it. All right, so here's our first example. We have a piece of sheet metal with an area of 22 square feet is submerged horizontally in 10 feet of water. Find the fluid force on the top side. All right, so when we're dealing with a surface that is submerged horizontally in a fluid, such as water, we do not need to use calculus to find the fluid force. And so in this case, since we are looking at a piece of sheet metal that is submerged horizontally in water, then we will use the following formula to calculate the fluid force. The fluid force is equal to the fluid pressure times the area of the surface. And the fluid pressure is equal to the weight density of the fluid times the depth of that surface in the fluid. And that will still be multiplied by the area. All right, and so let's start determining each of these values. Let's start with the weight density of our fluid. In this case, our fluid is water, and we are working with imperial units, or the US customary unit system, because our measurements are in feet. And so, when we're working with the US units, the weight density of water is equal to 62.4 pounds per cubic foot. All right, and so that will be multiplied by the depth that our surface, or in this case, our piece of sheet metal, is submerged into the water. And in this case, we are told that it is submerged horizontally in 10 feet of water. So the depth is 10 feet. All right, and so then that will be multiplied by the area of our surface. And we are told that this piece of sheet metal has an area of 22 square feet. So I'll write that in. We'll have 22 feet squared for our area. And so now we have all the values we need to calculate the fluid force. And notice that the units, we're going to have feet times feet squared. That will be equal to feet cubed, which will cancel out with the feet cubed in the denominator right here for the units of our weight density. And so the feet units are going to cancel out, and we're just going to be left with pounds as our units, which makes sense because we are calculating a force, a fluid force, which will be measured in pounds. And so 62.4 times 10 times 22 is equal to 13,728 with the units of pounds. And so 13,728 pounds is the fluid force on this piece of sheet metal that has been submerged horizontally in 10 feet of water. Let's look at another example. So here's our next example. We want to find the fluid force on the top side of a circular piece of sheet metal with a radius of 3 meters submerged horizontally in 4 meters of water. All right, so once again, we are working with a horizontal surface, so we don't need to use calculus yet. We are going to be using the formula that the fluid force is equal to the weight density of the fluid times the depth of our surface in the fluid times the area of our surface. And so let's determine each of these values. Once again, we will start with the weight density of our fluid, and we are working with water once again. And so since our units are measured in meters, we know that we are working in the metric system, which means we won't be using 62.4 pounds per cubic foot for the weight density of water. Instead, we are going to use the metric system version of that value, which is that the weight density is equal to 9,810 newtons per cubic meter. All right, and so that is the weight density of water when you're working with the metric system, and that's going to be multiplied by the depth. And so we are told that our piece of sheet metal is submerged horizontally in 4 meters of water. So the depth is going to be 4 meters. And that will be multiplied by the area of our surface. And so unlike the previous example, we are not explicitly told what that area is. We are told that we have a circular piece of sheet metal with a radius of 3 meters. And so we're going to have to calculate the area ourselves, but that's not going to be too difficult because if we have a circular piece of sheet metal, that means that it is shaped like a circle, then we can just calculate the area of a circle because we are given its radius, which is 3 meters. And so the area of a circle is pi r squared. And so since our radius is 3 meters, I'm just going to rewrite r squared to be 3 meters squared. Okay, and so now we have all the values we need to calculate the fluid force. Let's square this radius here. 3 meters squared will be 9 meters squared. And so I'm going to rewrite that, and we will have times 9 square meters. And now, similar to our previous example, watch what's going to happen to our units. We have newtons per cubic meter, and then meters times meters squared. Meters times meters squared will be meters cubed, which will cancel out with this meters cubed down here in the denominator. And so, all of the meter units are going to cancel out, which is just going to leave us with newtons, which is the unit of force for the metric system. And so everything works out here. We just need to multiply 9,810 times 4 times pi times 9. And so if we multiply those four values together, we will find that the fluid force is equal to 353,160 times pi, and the units will be in newtons. And so that would be the fluid force on the top side of a circular piece of sheet metal that has a radius of 3 meters, submerged horizontally in 4 meters of water. And so while this is a perfectly acceptable answer, there is an alternative answer if you decide to multiply pi by this value. And so you could also have that the force is approximately equal to 1,109,484.86 and some more decimals with the unit of newtons. And so if you multiplied pi by this value, this would also be an acceptable answer for the fluid force in this example. All right, so both of these answers would be correct. Let's look at a different example. So next up, we want to find the fluid force on a square plate with sides measuring 2 feet, submerged vertically 2 feet into water. All right, so now we are working with a surface that is submerged vertically into a fluid, and so we are going to need to use calculus. But before we look at the formula for fluid force when we are submerging a surface vertically, let's draw a picture for this scenario. I always recommend that you draw a picture when you're working with vertically submerged surfaces. And so I'll draw our water level, and then let's draw the square plate. I'm going to draw the square plate like this, and each of its sides are going to measure 2 feet. And so I'll label that. This distance right here is 2 feet, and this distance right here is also 2 feet. Okay, and then additionally, we know that this square plate is submerged 2 feet into water. So the distance from the surface level of the water to the square plate is also 2 feet. All right, and so now we have completed our picture that represents this scenario. We are now ready to calculate the fluid force. However, we're not going to be able to use the formula we used for the previous two examples because this surface is submerged vertically into the water. And the difference is that when a surface is submerged horizontally, the depth of that surface is going to be one specific value. However, when you submerge a surface vertically, there is a range of values for that depth. And so we can't use the same formula. Instead, we need to use a definite integral that will allow us to add up the incremental force over the range of values for the depth of this surface in the water. And that definite integral looks like this. The force is equal to the weight density of the fluid times the integral from c to d, which are the values of y that represent the range of values that the depth will be for our surface. And inside the integral, we will have a function h of y, which represents the depth at a particular value of y for our surface, and that will be multiplied by a function capital L of y, which represents the length of our surface at a particular value of y, and that will be multiplied by dy. All right, so when determining these two functions in our formula, we are going to need to look at a small rectangular region of our surface, right? So this will be our representative rectangle, and we're going to look at the fluid force for this representative rectangle and then integrate it for the entire range of values that we could pick that rectangle between, which would be the depth of our surface. And so in order to do that, in order to set up our bounds of integration, as well as determine the depth function and the length function, we need to set up a coordinate system in our picture. In other words, we need to place an x and y axis somewhere in this picture that we can then use to set up this definite integral. And there are many different ways to set up each of your axes. You can put the x-axis or the y-axis wherever you want. And if you want to learn more about that, watch my lesson video on this topic. But for this example, I'm going to let the x-axis be the surface level of the water, right? So I'm going to label this as the x-axis. And then I'm going to place the y-axis along the left side of our surface. All right, so this is the y-axis for this drawing. And now what that allows us to do is determine the range of y values that the depth of our surface lies between. Those are going to be our bounds of integration, right? And so since this surface is submerged 2 feet into water, we can say that this y value right here is -2. And then since one side of our square plate measures 2 feet, we know that the bottom edge of our square is going to lie at y equals -4, which would be 2 values less than -2. Okay, and so now that we have our coordinate system drawn here, let's start setting up our definite integral. We know that the fluid force will be equal to the weight density of our fluid, which in this case we're working with water, and our measurements are in feet, which means we are using imperial units, or the US customary unit system. So the weight density of water will be 62.4 pounds per cubic foot. All right, and that will be multiplied by the definite integral from C to D. Now these bounds of integration are going to represent the range of y values for the depth of our surface. Or in other words, the range of y values for which we can pick a representative rectangle throughout our surface. And so in this case, that will be from -4 to -2. So our bounds of integration will be from -4 to -2. All right, and so now we want to determine the depth function, h of y, and the length function. And so let's start with the depth function in terms of y. This represents the depth of our representative rectangle. And since I placed the x-axis at the surface level of the water, that means that the depth of our rectangle will be equal to -y, right? So h of y will be equal to -y. And that is because, let's say this rectangle is 3 feet below the water, we would move 3 units below the surface level of the water. And so 3 units below would be at y equals -3. And that would be the case if we were 4 feet deep. We would be taken down to y equals -4. And if our rectangle was 2 feet deep, that would take us to y equals -2. And that would occur for all the y values between -2 and -4. And so the depth of our rectangles is going to be -y. And so we can substitute that in for h of y in our definite integral. We will have -y times the length function in terms of y. Now the length function is going to be the length of our rectangles. And so notice that for the entire shape of our surface, that the length of our rectangles is going to remain the same. No matter where we draw a rectangle throughout this surface, it's going to have the same length of 2 feet. And so capital L of y is equal to a constant value of 2. So we will plug 2 into our definite integral, and that will be multiplied by dy. All right, and so with that, we have now finished setting up our definite integral that represents the fluid force on this square plate that has been submerged vertically into the water. And so if I clean up my work here, we can solve this definite integral to find the fluid force. And so if I pull -2 to the outside of the integral, we'll have that this is equal to 62.4 times -2. That will be equal to -124.8. And that will be multiplied by the integral from -4 to -2 of y times dy. And now we have a pretty simple integral that we can integrate and solve. And so if we use the power rule of integration on y, we will add 1 to the exponent to get y squared, and then divide by that new exponent of 2. And so this will be equal to -124.8 times y squared divided by 2, evaluated from -4 to -2. All right, and so now if we evaluate this expression at -2 and subtract the evaluation at -4, we will have that this is equal to -124.8 times -2 squared divided by 2 minus -4 squared divided by 2. And so now if I clean up my work here, we can simplify, and this is equal to -124.8 times -2 squared, which is 4, divided by 2, minus -4 squared, which is 16, divided by 2. And 4 divided by 2 is 2, and 16 divided by 2 is 8. And so we can rewrite this to be 2 minus 8. And so we'll have 2 minus 8. And 2 minus 8 is equal to -6. And so this is equal to -124.8 times -6. And if we multiply those two values together, we will have that the fluid force is equal to 748.8. And then our units are going to be in pounds since we are working with the imperial system, right, because we're using feet. And so the units of force will be in pounds. And so 748.8 pounds is the fluid force on this square plate that has been submerged vertically in water. So here's our next example. We want to find the fluid force on the vertical side of the tank shown below, where the dimensions are given in meters. Assume that the tank is full of water. All right, so in this case, we aren't necessarily submerging a surface into water. Instead, we're looking at the side of a tank that is filled with water, and so that side of the tank is going to experience a force from the water in the tank. All right, and so since we are working with a vertical side, that means we are going to need to use calculus, which means that we will use the formula that the fluid force is equal to the weight density of the fluid times the integral from c to d, which are two values of y, of the depth in terms of y times the length in terms of y times dy. All right, so now before we can use this definite integral, we need to set up a coordinate system for our picture here, right? So we need to place an x and y axis somewhere around this triangular side so that we can determine the different parts of our integral. And so before we do that, what I want you to notice about this vertical side is that if we were to draw a representative rectangle, I'm going to draw one right here. Notice that the length of that rectangle is going to be dependent on where you are throughout this vertical side, right? If I drew the rectangle further up here, it would have a longer side, and if I drew it further down, it would have a shorter side. And so because the length is not constant like it was for the previous example, and a triangle is a symmetrical shape, I'm going to recommend that you always place the y-axis through the middle of that shape. Right, so if you have a shape where the length of your rectangles is not going to be constant, it's going to change, and your shape is symmetrical, like it is right here, then you want to place the y-axis through the center of that shape, or of that surface, or of that side. Whatever you're working with, you want to put the y-axis through the middle. And so let's do that. I'm going to put the y-axis right here, and what this is going to allow us to do is determine the length of our rectangles a lot easier. Because what we can do, due to symmetry, is calculate the length from the y-axis to one side of the triangle and then multiply it by 2 to get the full length of all of our rectangles. And we'll look at that in a little bit when we actually determine our length function in terms of y, but let's finish setting up our coordinate system here and the other parts of our definite integral. Okay, so we still need to place an x-axis somewhere within this drawing. And so I'm going to place the x-axis at the surface level of the water, or at the top of the tank. All right, so I'm going to make this right here the x-axis, and I'll label that as such. All right, and so now I kind of covered it up here, but the length at the top of our triangle is 4 meters, right? Our dimensions are given in meters, so this distance is 4 meters. And since we're splitting that in half, that means that this x value right here will be x equals 2, and this x value right here will be x equals -2. And then in the same way, we are told that the height of our triangle is 3 meters, and so we know that this y value right here will be -3. Okay, and so now let's start setting up our definite integral. The force is going to be equal to the weight density of water. Now in this case, we are working in meters, and so that is the metric system, which means that our weight density is not going to be 62.4 pounds per cubic foot. It's going to be 9,810 newtons per cubic meter. All right, so that is going to be our weight density, but we don't really need to write the units here. And so then I'll multiply that by the definite integral from c to d. Now these bounds of integration are going to be values of y that represent the range of values for the depth of our side. And so in this case, the whole tank is filled with water. And so the depth of this side is going to range from y equals -3 to y equals 0. And so those are going to be our bounds of integration. Between those two values of y, we can draw representative rectangles for our surface that we will use to calculate the fluid force for the entire side. And so our bounds of integration will be from -3 to 0. And now we're ready to look at the depth function for this scenario. Now, similar to the previous example, I chose to place the x-axis at the surface level of the water. And so as a result, the depth function h of y is just going to be equal to negative y once again, right? The depth of our representative rectangles is going to be a negative value of y beneath y equals 0, right? So the depth function is equal to negative y when you set the x-axis to be at the surface level of the water. That's the advantage to placing the x-axis at that location. And so I'll put that in our definite integral. We'll have negative y, and that will be multiplied by the length in terms of y. And so now this is where things can get a little tricky. Remember that I said that we are going to use symmetry to help us determine that length, because we're just going to calculate the length of 1/2 of our rectangles and then multiply it by 2. So what I'm going to do is we're going to represent this distance right here from the y-axis to the side of our triangle or the side of our tank with x. And so that would mean that the length in terms of y will be equal to 2 times x, right? Because this distance on this side would also be equal to x, which means that the length of our rectangles would be 2x. However, we can't use 2x in our definite integral. We need to determine x in terms of y. We need to find an equation that represents this line or this side of our tank. And that line will represent the distance from the y-axis to that edge. And so in order to do that, we're going to need to use a little bit of algebra. We're going to look at the 2 points that this line will cross through and find the slope between those points, and then use that slope and one of the points to form the equation of that line. And so we're going to be looking at this point right here, which is at 2, 0, and this point down here, which is located at 0, -3. All right, and so we're going to calculate the slope between those 2 points. And remember that the slope is equal to y2 minus y1 divided by x2 minus x1, right? So we have the change in y divided by the change in x. And so this will be equal to the y-coordinate of our second point, which is 0. So we'll have 0 minus the y-coordinate of our first point. So we'll have -3 divided by the x-coordinate of our second point, which is 2, minus the x-coordinate of our first point, which is 0. So we have 2 minus 0. And so if we simplify, this is equal to +3 divided by 2, which means that our slope is 3/2 for this line. Now we can use that slope as well as one of these points to set up an equation for that line. And we're going to do that by using the point slope formula for the equation of a line. And that looks like this: y minus y1 is equal to the slope times x minus x1. And so if we use this coordinate point right here, 0, -3, we'll have -3 as our value of y and 0 as our value of x. Then we'll have y minus -3 is equal to the slope, which we found is 3/2, times x minus x1, which is 0 for that point, right? We're using this point, 0, -3. And so if we simplify, y minus -3 will be y plus 3, and that will be equal to 3/2 times x. All right, and so now we have the equation of this line, and if you wanted to solve for y, you could subtract 3 to the other side, but we actually don't want this equation in terms of x. We want it in terms of y, right? We want to know what x is equal to so that we can plug it into this equation right here. We want to know the length in terms of y, right? This equation for our line represents the distance from the y-axis to the side of the tank. And so we want to find that in terms of y and multiply it by 2 to get the entire length between 2 sides of our triangle, or the length of our representative rectangles. And so if I clean up my work here, we can solve for x by dividing both sides by 3/2. That would be the same as multiplying by the reciprocal of that fraction. So we're going to multiply both sides by 2/3, and that will give us that x is equal to 2/3 times y plus 2/3 times 3. Now those 3's will cancel out, and so we're just going to have plus 2, and so I will rewrite this to be plus 2. All right, and so now this equation is the equation of this line in terms of y, and so we can plug this in for x, and so we will have that the length in terms of y is equal to 2 times 2/3 times y plus 2. And so now we can place that in our definite integral for L of y. And so we will have negative y times 2 times 2/3 times y plus 2. And that will still be multiplied by dy. All right, and so now we have successfully set up our definite integral that represents the fluid force on this vertical side of the tank in this problem. And so if I clean up my work here, we can now solve this definite integral and find that fluid force. And so I'll start by pulling out -2 to the outside of the integral. And so if you multiply -2 by 9,810, we will have that the fluid force is equal to -19,620 times the integral from -3 to 0 of y times 2/3 times y plus 2 times dy. Now we can distribute this y through this quantity, and so if we do that, this will be equal to -19,620 times the integral from -3 to 0 of 2/3 times y squared plus 2y multiplied by dy. All right, and so now we can integrate each of these terms by using the power rule of integration. And so if we add 1 to each exponent and then divide by that new exponent, we'll have that this is equal to -19,620 times 2/3 times y cubed divided by 3 plus 2y squared divided by 2 evaluated from -3 to 0. All right, and so if I clean up my work here, we can simplify this expression a little bit. Note that these 2's will cancel out, and so we're just going to have y squared. And then 3 times 3 is 9, so we'll have 2y cubed divided by 9. And so I'll rewrite that. This is equal to -19,620 times 2 times y cubed divided by 9 plus y squared evaluated from -3 to 0. And so now we can plug 0 into this expression and then subtract the evaluation at -3. But notice that plugging 0 into each of these terms is just going to produce 0, because 0 cubed times 2 is 0, divided by 9 is still 0, plus 0 squared is still 0. And so what we will have is that this is equal to -19,620 times 0 minus the evaluation at -3. And so if we plug -3 into these two terms, we will have 2 times -3 cubed divided by 9 plus -3 squared. And it's important to remember these parentheses around the evaluation for -3 so that you remember to distribute that negative to both terms. Okay, and so if we simplify, this is equal to -19,620 times -2 times -3 cubed. -3 cubed is -27, so we have 2 times -27 divided by 9 plus -3 squared, which is 9. And so we'll have 9. All right, now -27 divided by 9 is equal to -3, so we'll have -3 times 2, and so we can rewrite this expression to be -6, and so I'll write -6. All right, and so if I clean up my work one more time, -6 plus 9 is +3, and that +3 will become negative, and so this is equal to -19,620 times -3, and -3 times -19,620 will give us that the fluid force is equal to 58,860 newtons. And it's in newtons because we are working in the metric system, because our measurements were in meters, and so the unit of force for the metric system is newtons. Okay, and so 58,860 newtons is the fluid force on the vertical side of the tank in this problem that is full of water. Let's look at one more example for this video. All right, so here's our last example. We want to find the fluid force on the vertical side of the tank shown below, where the dimensions are given in feet. The tank is full of gasoline, which has a weight density of 42 pounds per cubic foot. All right, and so here's the vertical side of our tank. It is shaped like a semicircle, and since it is vertical, that means that we are going to be using calculus to calculate the fluid force. Specifically, we're going to use the definite integral that we used in the previous two examples. And so I'll write that down. The fluid force is equal to the weight density of the fluid times the integral from C to D of the depth in terms of y times the length in terms of y times dy. And so now if we were to look at a representative rectangle for this side, I'm going to draw one right here. Notice that just like in the previous example, the length of our rectangles is not going to be constant throughout the entire side or throughout the entire surface, right? If I were to draw a rectangle up here, its length would be longer, and if I were to draw a smaller one down here, its length would be shorter. And so, because the length is not going to be constant and the shape of our side is symmetrical, we are going to place the y-axis through the center of our shape. And so I'm going to do that. This will be our y-axis, and so I'll label that. This is the y-axis. And then just like I've done for the other problems, I'm going to set the x-axis at the surface level of our fluid. And so I will say that this line right here will be our x-axis, and I'll label it as such. So that's the x-axis. Okay, and so now that we have our coordinate system drawn, let's start setting up our definite integral. First, we want to figure out what our weight density will be, and in this case, our fluid is not water. We're told that it's gasoline, and we're also given its weight density, which is 42 pounds per cubic foot. So we will have that the fluid force is equal to 42 pounds per cubic foot times the integral from C to D. Now our bounds of integration are going to represent the range of y values for the depth of our surface, or in this case, our side of the tank. Now in this case, we were told that the measurement from the top of the semicircle to the outer edge is 2 feet. And so that would mean that this y value right here is -2, since right up here is y equals 0, so 2 units down would be -2. And so it looks like the range of y values that represent the depth in the tank will be from y equals -2 to y equals 0. Right between those two values of y, we can draw representative rectangles that we would use to calculate the fluid force. And so our bounds of integration will be from -2 to 0. Okay, and so now we want to determine the depth function, h of y. And so just like with the previous two examples, since I decided to place the x-axis at the surface level of the fluid, or in this case the gasoline, that means that the depth function, h of y, will just be equal to -y. Right? If this rectangle is 1 foot deep into the gasoline, that means that 1 foot below the surface level would place us at y equals -1. And so whatever the depth of that rectangle is, we negate that value to get the value along the y-axis that represents the depth. All right, and so we can plug that into our definite integral. We will have -y, and that will be multiplied by the length of our rectangles. Now, once again, like with our previous example, we are going to be using symmetry to our advantage to calculate the length of our rectangles. We are going to look at the distance from the y-axis to the outer edge of the tank, which I'm going to label with x, and multiply that by 2 to find the length of a rectangle for this vertical side. So once again, the length in terms of y will be equal to 2x. Now in this case, how can we express this curve right here that represents the distance from the y-axis to the outside of the tank? It's not a linear function this time, right? It's not a line that we can calculate the slope of. Instead, we have a curve. Well, remember that we are working with a semicircle here, which means that this curve could be represented with the equation of a circle with a radius of 2, right? This measurement right here for the semicircle would be the radius of the semicircle, and it would also be the radius of the full circle if we had the other half of this semicircle. And so we can use an equation of a circle to represent this curve. Now specifically, we can use the equation for a circle that is centered at the origin, because if we were to draw the other half of this semicircle, notice that this circle would be centered at the origin because of the placement of the x and y axis. The x-axis goes through the center of that circle, or along the top edge of the semicircle, and the y-axis goes right through the middle of the semicircle as well. So this circle is centered at the origin, which means that we can use an equation of a circle centered at the origin to represent the semicircle here. And that equation looks like this. It's x squared plus y squared equals the radius squared. And like I pointed out earlier, the radius is 2, and so I'll rewrite this to be 2 squared, and so 2 squared is 4, and so the equation of this circle will be x squared plus y squared equals 4. And so what we want to do is solve for x in this equation, and that will give us the measurement of the distance from the y-axis to the outside of the circle, and then plug that in for x in our length function, which will multiply it by 2 and give us the entire length of our rectangles. Okay? And so I'm just going to remove this other half of this circle because we don't need that anymore. And now let's solve for x in this equation. If we subtract y squared from both sides, that will give us that x squared is equal to 4 minus y squared. And then if we take the square root of both sides of the equation, that will give us that x is equal to the square root of 4 minus y squared. Okay, and so that's equal to x, which means that we can plug it in for this x in our length function. And so we will have that the length in terms of y is equal to 2 times the square root of 4 minus y squared. Okay, and so we can plug that into our definite integral for the length in terms of y. We will have negative y times 2 times the square root of 4 minus y squared times dy. Okay, and so if I clean up my work here, we now have a definite integral that represents the fluid force on this vertical side of the tank that is shaped like a semicircle. All we have to do now is solve this definite integral to find that fluid force. And so before we look at how to solve this definite integral, I'm going to reorder the multiplication here. Instead of having negative y times 2, I'm going to have negative 2y. So I'm just going to rewrite that real quick. We're going to have negative 2y, so I'll write that in, negative 2y times the square root of 4 minus y squared times dy. Okay, and so now looking at this definite integral, it's a little more complicated than what we've been working with so far in this video. We're actually going to need to use u substitution here because we have a composite function, right? We have the square root of 4 minus y squared. All right, so we're probably going to want to set the inside function equal to u, but in order for u substitution to work, we need to make sure that the derivative of that inside function, or what we're going to set equal to u, can also be found within our integral. And so remember that when you take the derivative of y squared, that exponent is going to decrease by 1. So you're going to have y to the first power in your derivative. And we have that on the outside of that square root, which means that u substitution is going to work here. In fact, it's actually going to work very nicely because the derivative of 4 minus y squared is negative 2y, but we'll get to that. Let's first set this equal to u. So we'll have u is equal to 4 minus y squared. And then if we take the derivative of that, we'll have du dy is equal to the derivative of 4. And 4 is just a constant, so the derivative will be 0. And then the derivative of negative y squared will multiply that exponent down and subtract 1 from the exponent. So we'll have negative 2 times y. Now if we multiply both sides by dy, we'll have that du is equal to negative 2y dy. And now whatever du is equal to, we want to be able to find that within our integral. And if you look in our integral, we have negative 2y dy right here. And so we can rewrite this integral in terms of u. And so we'll have that the fluid force is equal to 42 times the integral from y equals negative 2 to y equals 0. Remember that these bounds are values of y, and we're going to rewrite the rest of it in terms of u. So just try to keep that straight. Remember that we're not changing our bounds of integration. And then we'll have the square root of u times du. Right? I replaced 4 minus y squared with u because that's what we set it equal to. And I replaced negative 2y dy with du because that is what we found that was equal to. All right, and so now we can integrate the square root of u. Just remember that we can rewrite that to be u to the 1/2 power, and then we can use the power rule of integration. And so we'll add 1 to that exponent and divide by the new exponent. And so this will be equal to 42 times u to the 3/2 power divided by 3/2 evaluated from y equals negative 2 to y equals 0. Okay, so 1/2 plus 1 is 3/2, and then of course we divide by that new exponent. Now if I clean up my work here, remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction, and so this will be equal to 42 times 2/3 times u to the 3/2 power evaluated from y equals negative 2 to y equals 0. All right, and so before we evaluate this expression at these bounds of integration, we have two different options. We could rewrite u in terms of y, or we could change our bounds of integration to be in terms of u. And I'm going to do that this time. I'm going to plug each of these bounds in for y in this equation to get some new bounds of integration in terms of u. And so if we do that, if we plug y equals 0 into this expression, we'll have 4 minus 0 squared. And so that will just be u equals 4. So our upper bound, if we rewrite this, we'll have 42 times 2/3 times u to the 3/2 power. And then our upper bound will now be u equals 4. And then if we plug in negative 2, And for y, we'll have y squared, or negative 2 squared, which is equal to 4. So you have 4 minus 4, which is equal to 0. So our lower bound will be u equals 0. All right, and so now we can evaluate this expression at u equals 4 and subtract the evaluation at u equals 0. Okay, but before I do that, I'm going to pull this 2/3 to the outside. This will be equal to 42 times 2 divided by 3, and that will be multiplied by u to the 3/2 power evaluated from 0 to 4. And so now if I clean up my work here, 42 times 2 is 84, and so this will be equal to 84 divided by 3 times this expression evaluated at 4, so we will have 4 to the 3/2 power minus 0 plugged into this expression, so we'll have 0 to the 3/2 power. And now 84 is divisible by 3, and so that's equal to 28, and that will be multiplied by 4 to the 1/2 power cubed. Right, we can rewrite the 3/2 power to be that value to the 1/2 power cubed, because if you multiply the exponents, you still have 3/2. And then 0 to the 3/2 power is 0, so we have minus 0. And 4 to the 1/2 power is the square root of 4, which we know is 2. So this is equal to 28 times 2 cubed. And 2 cubed is 8, and so we have 28 times 8, which is equal to 224. And then our units will be in pounds because we are working with imperial units such as feet and pounds. All right, and so the fluid force on this vertical side of the tank is equal to 224 pounds. Okay, and so with that, we are done with this example, and this was the last example for this video. And so if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.